Welcome to another deep dive on The Explainer. I'm absolutely thrilled you're here with us today. We are going to act as, well, basically technological archaeologists, uncovering the invisible infrastructure that actually powers our entire modern world. We're embarking on this fascinating journey detailing the evolution of connectivity. We'll start from the absolute basics of radio wave concepts and build our way up to the incredibly complex mobile networks that set the stage for literally everything we do on our phones today.
So think about this fundamental mystery for just a second. Right now, at this very moment, there are millions upon millions of mobile devices broadcasting invisible signals through the air, all simultaneously. How in the world do they not just crash into each other in a chaotic storm of static? Well, the core problem of wireless communication has always been exactly this. How do we balance massive user capacity and high call quality, all without interference?
Here is our syllabus for today's Explainer. We'll cover 1. The mobile communication problem. 2. The GSM cellular solution. 3. Inside GSM network architecture. 4. The shift to packet data. And finally, 5. GPRS and edge evolution. Let's jump right in. Section 1. The mobile communication problem.
Okay, so the ultimate goal of literally any communication system is to deliver the maximum amount of information from a source to a destination in the shortest possible time, without errors, and importantly, affordably. To pull this off, the industry realized they had to completely abandon the first generation of analog mobile networks. Why? Because analog systems simply hogged way too much bandwidth. Plus, they lacked basic security. Seriously, anyone with a radio scanner could just tune in and listen to your phone calls. Digital communication, on the other hand, that was a massive, game-changing breakthrough. It allowed us to convert human voice into ones and zeros, which enabled data compression, absolutely crucial error correction, and robust encryption. So finally, your calls actually stayed private.
But here's the catch. Even with digital signals, you still need a clever way to share the airwaves. We do this using what are called access techniques. The first method is frequency division multiplexing, or FDM. Think of FDM exactly like a massive multi-lane highway. Every single user gets their own dedicated lane, or frequency range, to travel on. It's just like tuning your car radio to a specific FM station. You get that frequency entirely to yourself while you're using it.
Now, this idea directly builds into our next technique, time division multiplexing, or TDM. If FDM is everyone getting their own highway lane, TDM is more like everyone sharing a single lane but taking really fast, highly organized turns. We're talking milliseconds here. The signals share the exact same frequency, but they're separated by incredibly precise slices of time. And this concept of slicing time was absolutely crucial because it paved the way for the hybrid approach used in the second generation of mobile networks.
Which brings us to Section 2, the GSM cellular solution. So how did the engineers take these access techniques and scale them up to support millions of users across the globe? The answer is a brilliant, absolute genius breakthrough called frequency reuse. You see, telecom companies only have a very limited slice of the radio spectrum licensed to them. To serve millions of people with those limited frequencies, you simply have to recycle them. The idea is to use the exact same radio frequencies over and over again, but only in distinct geographic areas that are separated by enough physical distance so they don't interfere with one another. To map this all out, engineers rely on the cellular cluster concept. A cell is basically the geographic area covered by one single antenna tower. We take these cells and group them into what we call clusters. Now, inside a single cluster, every cell uses a totally different set of frequencies. By ensuring that neighboring antennas don't talk over each other, we completely avoid what engineers refer to as co-channel interference. And the best part? You can take this cluster pattern and literally copy-paste it endlessly across an entire country.
Moving right along. Section 3. Inside GSM network architecture.
All right, now that we've mapped out the invisible airwaves, let's bring it back down to Earth and look at the actual physical hardware making up the backbone of this system. When you make a call, the signal jumps from your phone, which we call the mobile station, straight to the tower. That tower is part of the base station system, and it handles all the radio links. From there, the signal travels via physical underground cables deep into the core network, known as the switching subsystem. That's the part that figures out exactly where your call actually needs to go.
Let's quickly decode some of these acronyms so we're all on the same page. You've got your MS, the mobile station, right there in your hand. It talks to the BTS, the actual antenna up on the tower. Multiple towers are then managed by a BSC, the base station controller. But the real brain of the whole operation? That's the MSC, the mobile switching center. It routes your calls and constantly checks the HLR, the home location register. Think of the HLR as a giant, highly secure database that proves you are in fact a paying subscriber and knows exactly what city you're currently roaming in.
Section 4. The shift to packet data.
Now, GSM was a true masterpiece of engineering for real-time voice calls. It worked beautifully. But as the 90s rolled on, a massive new industry problem emerged: the internet. You see, GSM uses circuit switching. That means when you make a call, the network opens a dedicated, constant pipe just for you, and it keeps it open until you hang up, even if no one is speaking. But loading a web page isn't a continuous stream of data, right? You click a link, download the page, and then read it. Dedicating a full open pipe for that kind of bursty traffic wastes massive amounts of network resources. The solution? A massive paradigm shift to packet switching, which was introduced with GPRS. Packet switching chops your internet data into tiny little packets, sends them alongside everyone else's data, and reassembles the whole thing at the end. It's incredibly efficient.
But to make this packet switching a reality, engineers couldn't exactly just throw away billions of dollars worth of existing GSM infrastructure. That would be insane. Instead, they had to bolt new hardware directly onto the existing framework. They added the PCU to separate voice from data right at the tower. Then they brought in the SGSN to route all those new data packets, and the GGSN, which acts as the ultimate gateway out to the wider public internet.
Section 5. GPRS and Edge Evolution.
So, we have packet switching, but the network still needed more speed. To get it without eating up more radio bandwidth, engineers did something incredibly clever. They changed the actual language the towers used to speak to the phones. They upgraded the modulation. Older GSM networks used a method called GMSK, which basically sent 1 bit of data per radio symbol. But then Edge came along and introduced 8PSK, which maps data to 8 different phase shifts of the radio wave. It's absolute engineering wizardry. This effectively tripled the data density, sending 3 bits per symbol, and instantly speeding up the network without needing extra frequencies.
The result of all these upgrades was a massive, game-changing leap in capacity. Original GSM data limped along at a practical rate of just 9.6 kilobits per second. To put that in perspective, that is painfully slow. By introducing packet switching, GPRS bumped that speed up to around 40 kilobits. And then, by adding that advanced phase shift modulation we just talked about, Edge practically delivered 120 kilobits per second. It was this specific, massive leap that finally made the mobile internet truly usable for the masses.
And in terms of real-world performance, these networks weren't just fast, they were really smart. They introduced what we call dynamic coding schemes. Essentially, the network constantly monitors your signal quality. If you're standing right next to the cell tower with absolutely perfect reception, it smartly strips away error protection data to give you maximum download speeds. But if you walk into a thick concrete building or drive far away from the tower, it instantly adapts. It trades that top speed for heavy data redundancy just to ensure your connection doesn't drop.
It is truly incredible to think about. Every single time you stream a 4K video or instantly hail a ride on your phone today, you are standing on the shoulders of these engineering giants. We have gone all the way from basic frequency reuse to the packet switch gateways of GPRS and the complex phase-shifting math of Edge. So I want to leave you with this thought. How did these legacy breakthroughs lay the invisible foundation for the blistering 5G speeds we absolutely take for granted right now? I encourage you to think critically about the sheer amount of technology sitting in your pocket. Thank you so much for joining me on this deep dive on the Explainer. Keep